So hello, I'm Kornel Kisielewicz. I'm the founder and lead developer of Chaos Forge. We're a small company based here in Wrocław. We're challenged with a extremely difficult and crazy and commercially unviable task of building a custom C++ engine for an independent computer game. Custom C++ 17 engine in full 3D. While doing that and having the ability to do everything by yourself, because well, our company has the beauty of using not invented here as a positive thing. While doing that, we were able to do some stuff that is being done right now in the game development world our own way, and I think that in some places a better way. So this is one of the components that I'm trying to. The component that I'm going to show you today is a data-driven entity component system. And so data-driven, or maybe first. The game we're working on is called Jupiter Hell. It's a true roguelike. I'm trying to recently not use the word roguelike because it means something different now than it did 30 years ago. But generally a top-down turn-based permadeath randomly generated RPG game. It's a spiritual sequel to one of my previous games that I did for free, which name I'm not allowed to say because it's trademarked, not by me. So we're building a C++ custom 3D engine ground up for the game. The engine is planned to be generic, so we plan to reuse it in further projects that have more procedural generation in them. That's why we decided to go with something custom. So, first of all, C++. There are two things. C++ in game dev doesn't look like C++ in other areas of commercial development. And it's kind of like, my choice was because it's the C++ that I like. So in game dev, you've got the situation that, well, obviously, this one's common for any kind of application that right now uses C++. Performance is king. If you don't care about performance, why the hell are you using C++ at all? We also need stable frame execution time. So basically, we live in 16 milliseconds that we have time to render a frame. In this 16 milliseconds, we have to do everything, and we need it to be stable. So basically, we do not want to allocate dynamically memory in frame. We don't use exceptions. We try to use a data-driven code architecture. So thinking about cache all the time, thinking about things aligned in memory. We'll get to that in a moment. We love our plain old data types. There's a love and hate relationship with STL, because generally STL is considered not performant enough for game dev, because game dev doesn't care about special cases. Game dev doesn't care about executing a copy constructor if you can do a mem move or mem copy. And STL is designed in such a way that it gives some guarantees that we in game dev don't need. However, in my case, I'm in love with the STL as an interface and as a design idea, so what we had to do is rewrite the STL for our own purposes. We aren't the only idiots crazy enough to do that. Electronic Arts, one of the biggest game companies, also has their own STL implementation. However, during the time when I started the game, writing the game, that implementation was way beyond the standard, and we love ours, C++ 17. So yeah, contrary to game dev, I love my modern C++. As long as it's not object-oriented. So questions about those weird things that we do, we can leave to Q&A if there's time. Otherwise, just catch me somewhere after the talk and I can explain all those crazy things and why we did them. So there's a crazy amount of code. There's like 35 slides of pure code in this presentation. I'm not going to explain anything line by line. The amount of code is here so that after the talk, when I give you a link, you can browse through it and then like see the details. I'm just going to be talking randomly about code that I put on the screen, and unfortunately, because the best slides, the most interesting parts are at the end, and I really want to get to the end, so I'm going to skip really fast some things. So the title, oh, yeah, that's exactly what I wanted to say. Oh, and first the question, who here writes C++ for a living? Okay, and who here knows C++ to the level that he could say what's the difference between PR values and X values? Okay. I just wanted to know my audience. Okay, so there are two components to the title. There's something called data-driven development, and the second thing is entity component system. So data-driven development, I'm not going to go into that. There's a great talk on CBVCon 2014 by Mike Acton about it. We basically care about data and how the data transforms instead of doing objects and thinking about how objects interact, right? Data is king. The way we pass data in the program, the way we access it is very important. We think about continuous storage, so we want to have things aligned in memory, so when we go in memory after accessing components one after another, accessing data one after another, we need to make sure that they are aligned in memory so there are no cache misses. That's basically it. However, entity component systems, that get people confused in Warsaw, so I stole a few pictures for that. So basically, in an entity component system, it's a different way of thinking. Instead of object-oriented design, you think about entities and components. Entities can be abstract identifiers. So basically, it's just there to identify a thing in the world. It has no data by itself, at least in theory. And component, silence. And component is a set of data. So let's say a set of data could be transformation in 3D space. A set of data could be data for a bone in a bone system. So basically everything that you have about an entity in the world, you split into small data parts, and then you handle those data parts through components. And in a data-driven system, you pack those components as well, packed as possible. So basically you try to put those components one after another so that when you access it, for example, when you process transformations in a 3D scene, you want to access them one by after another and go through the array linearly. And a system is a process, for example, executed every frame that updates and manipulates those components. So for example, the process of calculating world space transformations in from local space coordinates. There's a great talk at GDC 2002, which is available online, at least the slides are available online, a data-driven game object system, which is considered one of the first entity component systems presented. So just to be clear about the ECS, I stole a slide from somebody else. This is a regular, how you would have object-oriented design of a computer game, right? We have an entity, a drawable entity, a dynamic entity. Those are inheritance, right? Static entity, item tree, walking tree character. Then we have a dancing sword, which is both an item and a character. Well, we're screwed in that moment because we would have to rebuild or, God forbid, do multiple inheritance. Never do that. So for those cases, instead, we use a component system that, for example, we have a character, a tree, a fire trap. We have a physics component, render component, AE state machine component, resource component, particle system component, and we just add those components to the ones that we need. So in our case, in our system, because we want to be very, I'm going to split this into two parts. First, I'm going to talk about how we organize the data, and then the more interesting part is how we use C++17 to make the interface kind of fancy. So we want to organize the data as packed as possible. What's the problem here? If a component, for example, if we have 10,000 entities in our game, 10,000 things that are considered an entity, and we have, for example, only 3 entities that have an AI component because everything else is static, then we could pack this in one array, but we would need some kind of indexing into that array, and this is what we're going to do. However, first, let's define our entity. Our entity is defined as 2 unsigned integers. Okay, this is like, you could do anything else about than unsigned. We did it differently, which reminds me, there's a lot of STL code here. I mean, I use STL functions, STL algorithms. Those are not performant enough usually for what we want because of some edge cases. We're using our custom data structures, but I translated the slides into STL so that it's easier to understand. But damn, this code is unreadable. Can you guys read this? Let's try maybe. Unfortunately, I have the pointer there, so. Oh, yeah, this will be better. So the handle represents our entity, and actually the handle itself is the index. It's the index into a virtual array of components. Why virtual? Because, as I said, not every entity has every component. The counter is to make sure the counter is being updated every time a new, because if we destroy our entity, we have an index that is unused. And if we create a new entity, we want to reuse this index. So we have a counter to make sure that if we store a handle somewhere, if we store an entity, if that entity dies and the handle stored is trying to access that entity, it will know that it's not the same one because it has a different counter. So first, global view, we've got this ECS thing. The data that it has is a handle manager. The one approach to ECS'es is that the handles are abstract. You don't create them. You don't destroy them. You just have, if a handle has, if a given index has a component, that means that it exists. If it has no components, it means that it doesn't. However, for game purposes, it's a very bad idea. Also, you have situations where you store an index to something, then it gets destroyed, then something else is created, and you think you still have a handle to that thing that was previously there. So we need some way to control creation and destruction. So we've got this handle manager that handles our handles. Damn, that sounds stupid. We've got a vector, let's say quote-unquote vector of component interfaces, which represents our components. That I'll explain in a moment. And we've got some kind of runtime type system to identify components by type. So if we register a given component, let's say it's named SeeNode, it gets put into this map of types into component interfaces, and we know that this interface handles the component. We use runtime here because we also, what we do is we store components independent of type by using type erasure. So this is just plain data. From the point of view of the ECS, he's got those arrays of pure data which he typecasts at given moments into the proper types. So this is a component interface. A component interface has two elements. It has an index table which tells us how to translate those indexes from the handle, from the entity, into points in the component storage array. And component storage can be thought of as a vector, but with type, which is type erased. Oh, unfortunately, due to this scrolling thing, now we don't see what's up there. Okay, so the handle manager, I'm not going to go into that. What we use is we use a list, a next free list over a list of counters, so we know that when we destroy a handle, we can always find which is the first free handle and reuse it. So this one's pretty simple. There's a create handle, there's a free handle. There's no rocket science here, so I'm going to just skip it. The component storage, because it's type erased, we store our constructor and destructor for the given class or structure that is being stored. However, as said, usually components are plain old data. We will have some examples further in the slides. There's also a case that we store the original indices because we want to be able to destroy a component by index. If we have 3 components in this packed array and we've got a shitload of indices, we want to know how to destroy the second component. So basically we need to know which handle actually owns it. It's not an expensive procedure, but it really helps in the long run. And there's obviously append. There's a pop swap thing. So basically, if we remove a component from the array, we remove it, we swap the last one, we update our indices, and this way removal is really fast, despite the fact that they are packed in an array. And we've got the index table. The index table, this is a simplified, like a abstract interface of the index table. Why do we use an abstract interface? Because we've got several implementations of the index table. The basic implementation of the index table stores an array which is as long as the biggest index, and basically is a lookup table into the component array. It's a pretty simple, right? And the other one is a hash table, which basically hashes the values of the indices and gives us the results in our component table. The reason why we have both is that this one takes a lot more memory but is a lot faster. The hash map approach is slower but takes up a lot less memory. So what we can do is, if we know that a given component is being very rare, we use a hash table for it. If we know that it's like very often, so for most components, then we use a lookup table for it. Sorry. So yeah, the flat index table represents the direct. Okay, if we would have a component that is in every entity in the system, we could use direct indexing from the handle. The handle has an index, we would directly index it, and probably that still wouldn't be good because we would have holes. No, we wouldn't have holes because it's present for every index. So yeah, this is like the basic implementation of the flat index table. We've got the implementation of the hashed index table, which uses an ordered map here, which is horrible. And let's get back to our like top level view here. So here in the bottom, which is barely visible due to the fact that the screen is so placed, here in the very bottom we have the way we access explicit components. So let's say we want to access a transform component from the ECS. We do an ECS with the given type. Type is being looked up, and we get the component as a pointer, where player here is a handle. Now the point is, this is not very like efficient. We could, for example, cache the lookup for the type and then ask for a given type, then we would have much nicer lookup. However, this is not the use case in ECS'es. In ECS'es, we assume that the basic use case is go through all the components and update them. And due to the fact that we've got them stored, packed up nicely, this is extremely fast. So the situation where we just want to get a single component from a entity is not very often. So let's move to the nice part, the API. So let's say this is our sample component, which we will be talking about. It represents a SeeNode. So we've got a few transformations, offset, a local transformation, and a world transformation. We have a bool, which is if it's visible or not. We do not inherit from anything. We do not need special fields in it. This is basically our component. So any kind of structure can be our component, as complex or as simple as we want to. We register it within the ECS by using just register component with the type name. We create a, okay, here's ECS, here's my ECS, that's my fault. So we create a handle for the, let's say, the player in the game. We just do a create, which creates us the handle, returns us, and everything like that. And then we can, for example, add a component. We do it by add component, name of the type, name of the handle, and the other parameters are being passed directly into the constructor of SeeNode. So due to the fact that in C++ 17 or even 14, we have the ability to construct structs by just using the universal constructor, we can directly pass them to a function. The function will be in a later slide. First, I'm showing the API, then I'll show the code underneath, right? Or we can, for example, due to the fact that we have a pointer returned, we can have a nice shortcut. We can, for example, try to get a SeeNode from the player, and if it exists, we actually do an update on it, right? Or, for example, run a for each, which is what systems are supposed to do, but the option is still there. We can run a for each, pass it a lambda, and for every element, we will do a, let's say, update of the world. Systems, on the other hand, are a little bit crazy, because systems usually in ECS is done in C++, they need to inherit something. Oh, those things are so complex that I cannot look at them. But we did want to have the ability to write both systems and components without including almost anything, and writing everything as plain code, right? If I'm writing a system, I do not care what it inherits from. I'm just trying to get as much as clean everything as possible. So you've got a free function. You've got a free method, which is not virtual, not anything, which is update. Let's say it updates the local value of the node with the offset value of the node. All the functions take time, which is sensible in games, but usually not used in every update function. And we have a metaprogramming language list of components. This is important. This thing tells us that the update function takes a SeeNode. We register the system just by passing the name of the type, and it automatically calls update when called, which is kind of funny because this isn't virtual, this isn't component array, and the type in the component map. And when we register a system, this is a bit more complex. Ugh. I'm losing my focus here. And when we register a system, well, we pass the system as a type, as you remember. We create the system passing those arguments into the constructor. We use an if construct to check whether it has an update, and if it has, then we register the update functions. I'll get to the registration of the update functions in a moment. And the same thing with if it has components, we register component updates, because update can both take a component list or be a pure update that is being run no matter of the components. And we return the results. But there's a question here. How do we created a type here. We don't know anything about the type. The type doesn't inherit from anything. How do we make sure that it gets deleted? Because we created here, obviously the user will not delete it. So here's a quick trick, completely unrelated to ECS'es, but very nice. We can make a std function that takes no arguments and returns void. We call it Destructor handler. And what we do, we have a vector of those Destructor handlers. And the thing that we do at the end, we place back a lambda that only does delete result. Due to the fact that it's type erased, it will call the proper destructor, and it will get cleaned up at the end, which is nice. This is kind of like a universal destructor. You can put anything into the array with a delete, with a lambda, with a delete, and you can destroy anything, no matter what kind of type it is. Okay. So, on to system registration. As I said, there's a if construct has ECS update, then we register ECS update. It's a construct thing, otherwise register ECS update would never be able to compile because it would tell us that the system we pass doesn't have an update. So this one prevents calls on the system without update to this function. And in this registration, what we do is we register a lambda that takes, because those ECS updates, they don't have components. Those are the easy ones. We basically register a lambda that takes time and runs this update with itself and the time. And we store them in an, register update basically stores them in an array of handlers, same way as the universal destructor did. It gets a little bit more complex if we actually register something with components, because we then have this, compile time list of those types that we are supposed to handle. So how we handle that is for each of those type we get the storage. So we look up their type only once. We don't want to look up in a loop the type every time. So we get the storage for every of those components using this magical function gather components. I'll get to that in a moment. And then we do a simple loop. This whole thing, when you run update, gets actually completely inlined, and it's the equivalent of actually running the loop on the separate components. There's no function calls here. This is extremely performant, which I'm really happy about. However, I would want to go into gather components. Unfortunately, I haven't found any nice way of implementing that, so it's a mess of templates. You can get into this code if you want to later, but I'm not trying to even explain it because it would take the rest of the talk here. So there was that for each. The for each is really simple. We also get the storage. We run it for every element. So this one was kind of easy to expect. The fact that we pass a lambda here allows us to write nice things in C++ 17. I like it. So, this is like what I showed is a generic ECS system. There are several different ECS implementations on the web. There are some C++ ones, some Java ones. Really? Okay, never mind. So we did a couple of enhancements to the ECS system with things that regular ECSs don't have, and these are the ones that I really wanted to talk about. So first of all, in almost every 3D computer game, you have something of a scene graph. A scene graph is a tree that stores relationships between objects, so that when you, for example, pick up a table, the laptop will move with itself, right? The laptop has a local position. The position is dependent on its parent. The table is its parent, so if you move the table, the laptop will move. That basically is a scene graph in like really few words. So we have to have a relationship between entities. We could do it over the component system, but due to the fact that it's so important and so like the heart of a 3D scene, we decided to build it into the handle system. So handles, apart from that counter and next free thing, they also store indexes for their parent, their first child, their next sibling, and previous sibling, in effect doing a tree that is being spanned over the entities. Obviously, entity, if created, does have no relationships, and it will be handled in the same performance way if it would have not had this system, as long as we don't use this system. So it's only, you pay only for what you use. This allows us, and obviously when we attach, we do updates of indices. We have an attach method, we have a detach method. We update those indices as needed. However, what can we do thanks to that? For example, we can go over every handle that is a child of the player, and let's say call ECS remove. The removes are, by the way, delayed, so that we do not get into a situation where we remove something and a previous thing accesses it, or we have like an iterator for a previous thing. So we have a delayed remove that is being called after all updates are done. And the second thing that we could do, for example, recursive components. Let's say the player has a vision node, the sword he's carrying has a vision node, the I don't know, his inventory has a vision node. Let's say we want to set all those with visible equal to false. We can do a recursive component lookup here. Or, for example, SeeNode, a typical situation in a scene where you want to check whether a node has a parent, and if it has a parent, you multiply the transformation of the local node by the parent node. So basically a typical update of a scene. And if it doesn't, it just copies its local position. Now, anybody who knows anything about computer graphics will probably see that there's some cheating here, because this only works if we already calculated the transformation of the parent. So how do we handle that? Well, we make sure that on every attach or detach, we reordered. Okay, first of all, some components are affected by that, and some of them are not. If they are not, don't care. If they are dependent on their parents, then we pass a special information that they are recursive. And if that is so, then if it's a relational component, then each time we add something or detach something, we make sure that the parents are always before the children. So in this component array, we swap places of components depending on whether it's a parent or a child. It doesn't, the amount of swaps needed after each detach or attach is only as long as the highest, as the height of the biggest tree in the relationship. So it's really fast. We keep those components basically ordered that always parents come before children. And this way we can do an update and make sure that if we update and get the component of the parent, that component will be already updated. Okay, recursive rebuild. Now this is another one, but why is this slide here? This is also an example of a component of a system. It's actually used in the game. However, oh yeah, Second thing that we did, obviously we have a couple of other things like void destroy. It also gets stored. So if we destroy a given component and it has to have some special thing ran on destruction, we can create a function for that, also free function, instead of writing a destructor or anything. And the second thing is we can handle messages within the system. So for example, we can say that if the system gets a kill message and that kill message is directed on the entity that has this ragdoll data, here is the message that is going to be run. As you see, it's also a freestanding function that has nothing to do with any kind of virtual inheritance, with any kind of inheritance or nothing, because it's also handled by the system that does the field detection. So the system, unfortunately, right now, it needs to be passed at runtime the list of all the possible messages. So we have like an enum to control everything. We have structure for message action, message update time, message update visible. Messages can have any amount of data. They are just plain structs, but they need to have a message ID. This message ID is used to make sure that if we cast a message, we always cast to the proper type. So here we can go downstairs. Yeah, so when we create the ECS, we pass it this message list. And then we can create a system that handles those messages. The easy case is one that doesn't have a component. Then it's just the system always gets this message if the message is being dispatched. And the second case is if we have a component, then it parses the component. It makes sure that the first element of the component is actually a handle of the owner, and then it runs this message on that given component. So what we can do is use this ECS to queue message action. 2 is the time that will pass before the message is being ran, and the message should be, and the first argument of the message is player, so it's being passed to, no, it was somewhere higher. It's being passed to this structure message action. The implementation details are that we treat all messages as, once again, type erased data, so all of them are stored in a payload character array and are being type erased. And we have a message cast that makes sure that when we cast those messages, they're being cast to the right type. And here we have the queue where we use the further arguments to pass to the structure creation. So we pass the name of the message, we pass the arguments in the function call, and we create this message without needing to create a structure in our own code. So this is done similarly to the update things. We've got some handlers that take a message. When we dispatch a message, we actually go through those handlers and run it on the given list of our handlers. And as said, further be dragons, because the registration function for the messages is kind of complex. What we use here, we use the MPL list of the messages to execute on every type register ECS component message, but we execute it only if has ECS component message is actually true. This is a kind of trick that is it's already not needed in C++ 17, but before C++ 17, to make sure something was called for every type, we could create an unused int array with a comma operator and 0, so this doesn't matter, but this is being only called for, this is being called for every message, but we use a true type or false type to detect whether we actually want to register this component message or not. Here be dragons. So this is the callback mechanism. We got our specific message, we got our list of components, and similarly to before, we gather the components and run only on the entities that receive this given message. We also have this possibility to run the message recursively, so that if a given entity gets a message, all of its children will actually get the message too. Okay, and this is a next advancement that we did, is we have a possibility to have a single entity have several components. This is kind of problematic in terms of indexing, so what we did, we are type erasing iterators into a type erased version. Here you have iterator, which uses line storage, uses 2 pointers because we don't need more. And index range is a pair of iterator, and then we can have this index table which returns a range, type erased, and it's being passed it again to know what the next one in the range is. We only use that for components explicitly, so if we want components that are capable of having multiple copies, then we use ranges, and if you have components that only have a single copy, we don't use those ranges, we use the faster functions to basically access them. But yeah, this is kind of messy when you're doing type erasure. Extraction, assignment, and creating a new index range using any kind of iterator. But multi-component support allows us nice things like for every item slot component in the player, do something with the item, or for all recursive components of a vision node. So basically, this is the same as previously, but now this will work for every node, not only the ones that. Okay, basically, recursive components checks whether it's a multi-component array or not, and runs a proper function of it depending on that. So this will still work even if multiple components are here. And for example, you can remove them one by one, because if you've got, let's say, 20 item slots in a single player and you only want to remove some of them, you obviously don't have a handle for them. So what you can do is, for example, run ECS remove component if, then do a check, and it only removes those components in the same handle that pass this given check. So there's still some work to be done, actually a lot of it, on the ECS. Let's zoom out for this case. Ooh, where's my mouse? Okay. So as I said, we reorder the components in our storage depending on what is apparent or not. Right now we reorder them by swapping, but what we could do is make sure that the parents and children are sticking closely together. So component reordering is a heuristic that makes sure that our access is as much linear as possible. So first of all, the scene graph could be held together, so we always are sure that the parent was something that's right previously and not like on the beginning of the component array. The second thing is we could store multi-components as blocks. Right now they are randomly assigned in the array because we usually access them linearly, but we could store them so that they always make a block. This has some cases with deletion and insertion that are very complex, so we didn't do that yet. And finally, we could do it so that a given component has during creation an information that is dependent on a other component, and it makes sure that when they are accessed linearly both, so they go together for the array. This is not yet done. However, in most cases, we have the storage the same because two components that are dependent, usually they are both present, so when we remove them, they land in the same places. And there's also other performance updates that we could do. Virtual memory is one obvious thing. We use right now vectors without virtual memory, but with virtual memory this could get a lot easier because we wouldn't have to copy those components after we make the array bigger, right? There's some nice information on that. However, there's no language level support, so you have to implement it for every platform independently. And the model that we use, we do not use concurrency right now, but it's perfect for parallelism. You know exactly that those updates are independent. You can run them in as many threads as you want, and this is something we'll do in the future. But right now, due to performance, the performance is good enough that we don't need it, so I don't want to worry about all those issues related to parallelism. So, for anyone interested, I'm streaming this development of this game live at Twitch on the address given here. And what I did is I ripped off the whole ECS from the system. I simplified it a lot, removed some things that are like still in production, and I put it on GitHub. So if any one of you wants to see the code, it compiles, but I'm not giving any guarantees it works because I had very little time to do that and obviously didn't have time to test this one iteration, so it should be more considered as a learning material. However, if you want to build something based on it, it's under the MIT license, so go ahead and use the code. We plan at some point probably releasing the whole of the engine, at least the library support part under MIT, but no earlier than the release of the game itself. Finally, you can follow me on Twitter. You can check out the game at jupiterhell.com. And thank you very much. I think we do have time for questions because the person responsible is not here. So if anybody has any questions. Using variant? Okay, but if you're using variant, you have to explicitly name the types that you're going to erase, right? In the library, we have the ECS, right? And in the game, we have the components we are going to use. So the library would need to know exactly what components the game will use to have a proper variant for that. You know, the problem here is the more abstraction you do with the templates, the more problems you will have later on. Also, like, you would have to provide them in one single place. Right now we have a situation that part of the ECS is created in a... Okay, here's a spoiler. The game works in ASCII on a Linux terminal also. It has a separate interface for ASCII. This is like a completely separate module. So that module registers some components, and the graphical one registers his own. So then both of those would have to first agree upon a common amount of components, and you would have to put all those components into one file to create that variadic, I mean, to one, include them into one file to create that variadic variant, right? Yeah, or have two versions, or it gets complex, basically. I'm feeling bad that we need to pass the messages as a list, because I would want them to too be able to register additional ones.
Yeah, do you, for type release, do you use boost penalty or your own?
Boost? If I would add even a single line of boost, this whole code, instead of compiling in 25 seconds, would compile 4 minutes. So yeah, we're not using STL, which is slow because it has a lot of code that's not needed. We're not using Boost because it's slow. Our whole engine compiles in a couple, like below 30 seconds because of using only custom containers and not using any kind of template libraries, which is very important for game development because you have to have a quick, compile, check, change, compile, check, change pipeline. You mean the ECS or this ECS? This ECS. No, right now we're building it in-house. This is like the first public version that I've put, and it's only for demonstration purposes. But at some point we want to put it out, and probably under MIT also. So if somebody will want to work on it, sure, but they will get no support. Because obviously, the difference between creating a game engine for commercial purposes and creating a game engine is that for commercial purposes, you have like 4 times more work because you need to write documentation, you need to provide support, and the worst thing of all, you need to provide API compatibility. Right now, we can change something like within a day, completely change an API for a given thing, and we like that. But if we would already like put out the engine out there, people would scream, you're breaking API compatibility, and this is no way to work. I know there's a lot more to be churned out in terms of compile times, but at the moment, you know, as long as we're sub-minute for a full rebuild, we do not care about that anymore. Okay, so thank you very much again.